Recording.
All right, so the first problem we're going to tackle here asks us to find the element that appears once in a sorted array, where all other elements appear twice, one after another. Find that element in O log n complexity. So they give us an example here, where the input is this array full of integers that are sorted. We have 1, 1, 3, 3, 4, 5, 5, 7, 7, 8, 8. And the output is, of course, 4, since it's the only one that appears once. Okay, so let's go through what is given to us. So we are given an array. So this is array, we say a sorted array of ints or integers. So our input is a sorted array of integers. Our output is basically an element, an integer that appears once. So it's not a duplicate, it doesn't have a pair. So that is, that's our input, sorted array of integers, and this is our output, an integer that appears once. Okay, cool. What's our complexity or our constraints? Let's write that out. So let's see, complexity. Our complexity is O log n time complexity. So we need it to be O log n. Okay? O log n time complexity. Okay, cool. So that is another one of our conditions. Cool. Now, let's see here. So the first thing that I think of when I think of O log n is binary search. And how binary search works, it's a way of dividing and conquering. So you look at like one half and disregard the other half, and then break that half down into sub-halves until you find what you're looking for. That's essentially what we want to do here. That's like, we're cutting the amount of times we need to be looking or iterating over subsets, basically. Instead of iterating over it, I don't know, that's like 12 or something times, we would iterate it over it like 3 times instead, because we do it log n. Actually, I think there's 11 here, so it'd be like, I think like 3 iterations or something. All right, so let's go a little deeper here. So the thing with binary search is it usually requires a target. So we don't know what the target is, right? So we're going in blind, so we have to modify this somehow to make it work for our purposes. So what do we know about the input? Well, we know that all of the integers in there are going to have pairs. They're all going to, all of them but one, it will have pairings that are identical. So we can assume that each, like the even indices and we can use the indices, so even indices and odd indices, we can use them to sort of frame this binary search. Basically, how we could go about it is we'll take the index and we'll ask if that index is either even or odd. If it's even, we're going to do some logic where we search one half. If it's odd, we're going to do some logic to search the other half. And that's how we're going to divide and conquer this bad boy. So let's get into it. So I'm going to sort of stub stuff out here. Let me use a purple. I like purple. So we'll call this search. Let's call it search. And it'll take in an array, a sorted array. And we want to take in a couple other things, because with this particular binary search, this is going to be a recursive function. So we're gonna be feeding into it not only the array when we recurse it, we're also going to be feeding into it a low point and a high point, which that will be the range of what the search will go through. It will go through a certain low up to a certain high, and that will be dictated if it's even or odd, and if the elements match or they don't. So let's go deep into this. So we'll have a low, and we will automatically assign it a starting value. We'll say it's 0, the beginning of the array. And then we'll give it a value of high, a variable called high, and its value will be the array dot length minus 1, being the last value of the array. Okay, so what the other thing about binary search, right, it's you have to get a midpoint. You have to establish a midpoint so that way you know which half you're now looking at. So we are going to do something like that. We're going to have a variable called mid, and we're going to put it down here. Say let mid. And basically for the mid, we are going to say, we're going to math.floor, because we don't want a floating point index, because the mid is going to serve as our index. And we're going to pass in our low plus our high divided by 2, because binary, half, you know? So we're going to cut it in half. So then this will give us the middle index, which in our example, if it's 11, let's see, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So can I do basic math here? That's 5, and that's 5. Okay, so this is like our midpoint starting out. It'll be 5. This 5 right here. And that is what index? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's the 5th index. So we would grab this, and it'd be like the 5th index. And we want to then do some comparisons. We want to say, if the mid index, and we're going to do modulo here, so modulo 2 is truly equal to 0, which basically means is this thing even? If it's even, we're going to do some logic. Else, if it's odd, we're going to do some other logic. And that's where we're going to have our different recursive calls. Okay. Now, the other thing we want to do, like each time we do this recursive call, we need to have a base case. to exit the loop, right? We can't keep on just doing this because it'll just keep on going forever and ever and ever. Yeah, sure, we're getting a midpoint, but so what? We'll just keep going. So we have to have some kind of exit logic. So basically, what do we know? When we're inside our if and our else statements, we're going to be manipulating our low, and we're going to be manipulating our high. And so when we do that, the low may get bigger, and the high may get lower. So we have to say, if the low is greater than the high, return null, because that must mean that we've already covered everything. And if we've covered everything up until now and we haven't found anything, we just have to return null. So that's what is going to be one of our base cases. So this is the case when there is no like everything has a duplicate, so you just return null. So there isn't just one that has, occurs once. Okay, so we'll say if the low is greater than high, then we're going to return null. All right, that's cool. So that covers the case when there is nothing there, right? Everything's a duplicate. But what about when there is a duplicate? What do we do? So when there is a duplicate, what we want to do is, or if there's not a duplicate, we want to say if the low is equal to the high, then we're going to return that element at that position, at array at the low, because low and high are the same one. You can choose either one. But this basically says, okay, if they're equal to each other, then it must mean that we have traversed each side, we've looked at both sides, and now, or at least we've searched enough to now know that this is all that's left. It's just this one element left. So it must be alone. So we return that guy. So the logic inside of this, if it's even business. So basically what we want to do here is now ask if the array at the midpoint is truly equal to the guy at the mid plus 1, because we assume that if like we started, I don't know, let's say at 2, for example, at the even point is when the pairing begins, and at the odd point is where the pairing ends. So this would be the pairing. So we say, okay, if it is even, then the next guy over, then it must be its pair. So we say, if that is true, that it is equal to it, then we're like, okay, so let's go look, let's continue to do our recursive call. Because now we don't want to look at mid plus 1, we want to look at mid plus 2, because mid plus 2 means we're gonna look up the array. We're going to look further. So these guys are equal to each other. So we've already compared them. Let's move to the 4th position, and then let's continue from there. So basically that's what we want to do next. Just checking the time, making sure that I am all good. Okay, cool. So then we're going to say that is going to be our new low. So we'll say return the search, passing in the array, and mid plus 2 and high. Because we assume that since we've already looked here and these guys look good, then that must mean we need to look further up ahead to start comparing stuff. If these turned out to not look like each other, then we would say, oh, so if this even guy I'm on here, if his odd doesn't look like him, then it must mean the one behind him must look like him. So if that's the case, if they aren't alike, then it must mean that we have to go the opposite way. We have to make our high be mid minus 1 and make our low just be equal to 0. So that will be the else condition for this statement. If else, getting kind of cramped here, if else we're going to return the search from the array from low to mid to low to mid. Right. Rather, excuse me. Yeah, low to mid. So in this else condition, this is the else condition we want to do the this is the else condition where we want to actually say to look behind us, the mid minus 1. So on this line, we are just passing in low and mid instead, because if it doesn't look like it's adjacent guy, then we want to look behind it. So we're going to say, let's look from where I am right now as the mid, make me the high, and let's look below us and start comparing, because something's amiss here. So that's why we do that. Else, then we're going to compare the guy behind us. So if the mid is truly equal to the guy to the left of us, then we're going to do something. So then we're going to, if that's the case, if the mid is equal to the guy behind us, then we know that we want to, I have 2 minutes left. Then we want to look ahead 1 instead. We want to make our low be the mid plus 1, because we've already looked behind us and established, okay, this is a pairing, but let's not look behind anymore, let's look ahead. Let's look ahead to do the comparison. So then we want to return the search at array at the at the mid plus 1 and the high. Else, let's get real squished here. Else, we want to return the search from the low to the mid minus 1, because we've established that the guy behind us doesn't look like the current the current middle point we're on. So if the guy behind us doesn't look like that, then there's, again, something amiss. So now we have to make the guy behind us, the guy to the left of us, the new high. We want to then make sure that that section down here is the one that we focus on. Instead of going to the right, we go to the left. And this would solve the problem. This is in O log n time, because what we're doing is we are creating subsections to iterate over and then break in half and then repeat over and over again until we find what we're looking for. And that is the divide and conquer method, and that is O log n, and that's the problem.